is equal to IL receiver times delta R minus R receiver. Okay? So I can put this over there. And then I can actually write this reciprocity theorem in greater detail. If I write this in greater detail, then what I should have is that, as I have done in my lecture notes, then I can re-express this thing, power received, in terms of something like this. The 1/8 factor is still there, and then the voltage received is just equal to E incident at the exciting dipole okay, divided by I squared. I need I squared because I put in I in here. This I just assume it to be I. I divide by I squared to make this into E received, and then divide by R radiation. So this is my P received. And let me see what I have next. Then I can also calculate the power radiated, okay, that I have written down just now due to a current source. I can also write this quantity as 1/2 eta, the far field of radiation picked up by this sensor antenna over here, okay, which is I LR squared, okay, divided by 1/I squared L squared. Okay, this is just actually normalized. I write this so that this becomes part of this. This becomes part of this. I'm going to assume that LR is equal to L transmitter is equal to L. So the normalization just is equal to L squared. So I can also write the power radiation density in this fashion. Okay. And also compute the directivity using this formula. And as usual, then the directivity theta phi is equal to R radiation theta phi using this formula divided by power radiated. In total, this is the total power radiated divided by 4 pi R squared. Okay, so the directivity is given by this formula over here. And as I said, the power radiated is given by that formula over there. Then what I should have next is that if I were to plug this in here, I get the fact that the directivity is equal to 2 times S radiation because of these 2 coming from here, times the radiation resistance because of the radiation resistance coming from here, times I squared. I squared is just some quantities that I have inserted, and this is going to be the new directivity formula. Okay. And I can also actually model the power picked up by the sensor over there. Okay, the power picked up by the sensor over there. If I were to make this L sensor to be pointing in the theta direction times L, you will pick up the theta component of the field. Okay, actually this formula works for is actually polarization dependent. If you look at the detailed derivation, Maintainer aperture formula is polarization dependent. So if I pick up this field with this kind of a dipole, then I can write that the power received on the theta component, okay, on the theta hat component, is going to be equal to 1/8 using this formula that I had derived before, okay, E radiation dot theta hat square over R radiation times L squared. It's in L squared here. Okay, what I have done is actually to replace what I have in the numerator here. The numerator I said was previously equal to this, something proportional to this. Okay, by reciprocity you can replace it with something equal to that. Okay, hence the numerator can be, by the use of reciprocity, be replaced with something that looks like that. So the power received in the theta polarization can also be written like that instead of like this, okay? Just by the invocation of the reciprocity theorem. Okay? So I can write the fact that let me give you some homework.天下阿印。But I can also write the radiation power, okay, picked up by the theta component of the dipole to be equal to theta phi, assuming that the sensor is theta polarized as 1/2 eta E radiation dot the theta hat squared. Okay, I can also write this power we picked up over there, or this quantity. It was earlier picked up by an arbitrary dipole. If this arbitrary dipole is pointing in the theta direction, then this is the power radiated. Okay. And as I said before, I can use this formula and this formula together and rewrite the power received theta. The power received for the theta component being equal to 1/4 eta S radiated in the theta component being the component that I picked up times L squared over R radiation. Okay? So if I combine this formula with that formula, I get a new formula for power received. You can repeat this for the phi polarization if you want to, but what you have then is that you can show that you can also, if you repeat this exercise with the phi component of the polarization, okay, you will have something that looks something like this. Assuming that you're picking up the phi polarization, theta phi L squared over the radiation resistance. Okay? Then you will have the total power radiated would be the theta component radiated plus the phi component radiated. Okay, just sum over the two. And then it should be equal to And then you can write the total power received. Theta component, phi component is theta half P received phi, and then 1/4 theta times S radiation theta phi L squared over R radiation. Okay, you will have this total power being received. And then we go back to using this formula again for directivity. From this formula, you try to eliminate the radiation power intensity and put the directivity in there. Then you will have this be equal to 1/8 eta L squared I squared d theta phi 1/4 pi R squared. Okay, just plug this formula back in there to eliminate SR theta, so you have this power received being expressed in terms of theta and phi with the directivity d. Okay, but the power received can also be written as effective aperture times S incident. This is just a definition of what an effective aperture is. Okay, just like radar cross section. Radar cross section, you just define the effective cross section so that the power incident is intercepted by the effective cross section. Then power received is also defined by this. So if you use this definition, and the fact that S incident is equal to 1/2 eta E incident squared. Okay, you can replace this with that, and then when you compare,
what is it? Is it the efficiency?
eta is the free space impedance. Okay, eta is and S is usually 1/2 eta E squared for a plane wave. Okay, that is the eta. Okay, so if we make use of this formula, then you're going to see the effective aperture formula coming in, but you have to do one more thing. You assume that this is a small dipole. It radiates to the antenna structure with a small dipole, and that the incident field from that small dipole incident square is omega squared mu I L squared. This is a Hudson dipole, 16 pi squared R squared. You assume that this is a Hudson dipole. The Hudson dipole radiates the field that is proportional to beta I omega mu I L over 4 pi R e to the I k R. This is what a Hudson dipole radiates. If you use this formula and find the amplitude of the incident field, you get this formula over here. Okay, so incident field is equal to that. You plug that in. Okay, and then you will have all these R squares canceling each other. R squared canceling each other. Omega squared still remains there. And if you equate the two sides now, then you end up with the effective aperture formula. Okay, you plug this in. You have AE, you have D. And then you will have this effective aperture formula. AE is equal to lambda squared over 4 pi p. Okay, this is assuming no loss in the antenna, and then of course when you have loss, then you actually have to put in some efficiency of some sort, like E times D, and this is called G, the gain of the antenna. And of course, the efficiency drops when you have very, very low frequencies, because the radiation resistance will become very small and very difficult to mesh to. And hence, you have this kind of problem. So this is essentially the general outline for the aperture of an arbitrarily shaped antenna. Okay. Are there any questions regarding this derivation?
assumption that you had when you calculated the per incident and effective, the quasi-static assumption,
Right.
is it always valid or the length should be much smaller?
You have to assume that the antenna structure, at least where you model with circuit physics, okay, that part has to be small compared to wavelength. I can have a half-wave dipole, for instance, where that thing is not valid. Okay, I have a half-wave dipole, where this is on the order of wavelength. This is order of wavelength. But then if I focus my attention on this part, and let me call that this half-wave dipole is excited by Hertzian dipole. And if I focus my attention on that part, I believe that the voltage at this Hertzian dipole would still be E incident times the effective length. Okay. But then the E incident is not the E incident due to this dipole alone, but due to multiple scattering that scatters into it, due to the environmental change that alters this E incident. Okay, that alters that part. And I think that you can still use the long wavelength argument for that little gap over there. Okay. So I think the proof will be still valid. Let me think about this actually. Here I actually assume that this is coming from that dipole over there, and that actually assumes that there's no environmental scattering. There's no environmental scattering into this, and this proof might not be valid for general environment. I have to think about this. Okay, but this is the proof that I have arrived at. Okay. Okay, let's go to problem 2A. I think most of you didn't get this part, 2A. Let's go to problem 2A.
And what's the answer to the third part of this question? How do you control the growth?
To control what?
How do you control this growth of manifesto?
Oh, the third part is due to the fact that when you have very long wavelengths, when the antenna is receiving, if you have an antenna and it is receiving some incident field, the model of the circuit model of this antenna is that you have you can have the inductive part. Okay, you can have maybe in general it should be something like this. And then you have a voltage source. That incident field induces a voltage drop at a gap. Okay, you can think of this incident field, you have a gap. And you can put a load here. You put an impedance of ZL at this gap. Okay? And then this could be the circuit model you use for that part of the antenna when it's receiving. This is something like the voltage is A incident dot L effective kind of thing. Okay, the voltage is something like that. Okay, this is a circuit model for the antenna in its receiving mode. Because it's receiving, it will be inducing current there, it will also radiate. So you have to add in the radiation part. So you try to match this antenna so that the inductive part cancels. So finally what you have will be something like this. Only the radiation resistance left. And then the load left, that is the resistive part, because it assumes that the inductive part cancel each other, or conjugate matching. And then you will want this to be equal to that. But the radiation resistance is something that drops rapidly with frequency. If the frequency becomes very, very low, the radiation resistance also becomes very small. Okay? R radiation is proportional to omega squared. Okay, so when you make the frequency very low, it's very hard to match this system. And then invariably other kinds of losses come in, antenna losses comes in. Okay, antenna losses will come in, R radiation will be very small, and then you try to match the system. Okay, you will match with something where the load is equal to R radiation plus R loss. This is maximum matching, like called maximum power transfer. But R loss starts to dominate over R radiation. And that you're not going to have the correct matching. And hence a lot of power will be dissipated in the lossy part. Okay. Okay, and hence the gain drops, the efficiency of the antenna drops. Antenna drops, and then even when lambda grows large, this thing remains finite, aperture remains finite. Okay? Okay, let's look at the part of this thing. Okay, this is quite an interesting part because quite also puzzles me as to how to derive this property. So we have this gamma k naught being equal to the imaginary part of 2k 1 over k minus k naught plus 1 over k plus k naught. Okay? And this is something that we like to sum over. And we would like to sum this over all possible n-wave directions and all possible polarization. And this one only becomes an integral. The two polarization becomes a factor of 2, and then the summation becomes equal to 8 pi cubed dk gamma k naught. Okay, k naught. And gamma k naught is that quantity above. Okay, but since gamma only depends on k, I can convert this integral into 0 to infinity 4 pi k squared dk. Okay, the spherical coordinate part to be integrated out, and I only have the radial part to integrate. So this I finally is equal to 2 times v over 8 by pi cubed, 0 to infinity. Let me cancel the 2 pi's. If I cancel them out, then I would have something like v over pi squared kind of thing. Okay, this 4 pi cancels with 8 pi cubed, and then I have v over 4 pi out there, and then I will have k squared dk, imaginary part of 1 over 2k, 1 over k minus k naught, plus the other part. Okay, this has 2 parts. Plus 1 over 2k, k plus k naught. So that integral looks something like that. But I think all of you did Cauchy principal value integration incorrectly. Okay, and I think some of you did it differently, but you got the right answer with the wrong technique, I think, because this can also be written as, let me see if you combine these two, this can also be written as imaginary part of, if I were to combine it, k plus k naught, k minus k naught, 2k, 2k, so this is over k squared minus k naught squared. Did I combine it correctly?
It's 1 by k squared.
What is that?
It's 1.
1 over k somewhere?
No, it's 1 by the numerator is just 1.
Just 1? Okay, just 1. Okay, let me see if it's correctly done. K plus k naught, k minus k naught. Yeah. Okay, it's 1. Okay. So, some of you did it directly and say that if I combine the two, this integral can also be written as 0 to infinity k squared dk imaginary part, or you take the imaginary part outside, which some of you did, 1 over k squared minus k naught squared. And then start to write this as b over pi squared. Some of you never did this, but some of you did. Minus infinity to infinity k squared dk 1 over k squared minus k naught squared. Okay? And then some of you start to do Cauchy principal value integration and detour this contour. But this is not allowed because Jordan's lemma is violated. K squared in the numerator, k squared in the denominator, that's not allowed. Okay? And so you start to detour this contour and pick up the poles. You assume that the poles are over here and over here. You pick up one of the poles, you get the correct answer, but you throw out the part of the infinity which is undefined. Okay, because there is the part that is undefined that you throw out. If you ignore the fact that Jordan's lemma is not satisfied. In order to satisfy Jordan's lemma, the numerator has to be 1 order less than the denominator. Okay? So it's a very, very interesting thing because Jordan's lemma is violated. You go ahead and do the integration, you get the correct answer, but the method is wrong. Okay? The correct way to do this problem is actually this way. That you combine these two integrals. You combine these two integrals into one. K squared dk, imaginary part of 1 over 2k, or k minus k naught. You can show that this part is actually 0 to infinity, but then if you change minus k to k, then everything flips properly. You can combine this semi-infinite integral into one infinite integral. You can show that to be true. You want me to show the detail, or you accept this fact? That this part can be combined with this part to have an infinite integral instead of a semi-infinite integral. Okay? And then you make use of the fact that this is going to be real. Okay, so if you take the imaginary part of 1 over k minus k naught is going to be a complex number, k naught prime plus a k naught double prime. If you take the imaginary part of this, then you will have something like k naught double prime over k minus k naught prime squared plus k naught double prime squared. If you take its imaginary part, that's what you're going to get. You want me to show you this detail, or this is acceptable? Okay. Now if you plug it in and replace this with this integral, okay, this k cancels with that k, so you have actually k dk, k naught double prime over k minus k naught prime square plus k naught double prime square. Now Jordan's lemma is satisfied. The numerator grows faster than the denominator grows faster than the numerator. So you can deform the contour. You can deform the contour. Okay, you can deform the contour. And then there will be poles at two locations. The locations of the poles is equal to k is equal to k naught prime plus or minus I k naught double prime. Those are the locations of the two poles. Okay? And then when you take the residue of this term, then they will be equal to v over pi squared. And then if you take the residue, this would be at the pole location. Okay, let me see if I did this correctly. Okay, what you do in taking the residue is that you factorize the denominator. So the denominator is factorized as equal to this plus I k0 double prime times k minus k0 prime minus I k0 double prime. Okay, factorize the denominator as such. You take the residue about, say, so actually the pole is not like that. The poles are like that, sorry. The poles are like that. Okay, the poles get squeezed out from top and bottom. Okay, not left and right. So if you take the residue, you can either detour the contour upward or downward, doesn't matter. Jordan's lemma is not violated. So you can pick up this pole or that pole. Let's pick up the top pole. The top pole is given by this term over here. Okay, pick up 2 pi I by the residue, but then in the denominator you also have this being equal to k naught plus I, so this becomes 2I k naught double prime kind of thing. Okay? Times this thing. And this thing contributes to 2 pi I, this thing contributes to that. And that k0 double prime cancels that one. Okay, that thing cancels that one. And according to my lecture note, finally this thing gives rise to d0 k0 prime over 2 pi. Okay, something like that. Okay, so you have to make it satisfy Jordan's lemma before you can detour the contour, and a number of you did not make it satisfy Jordan's lemma. So I took some points off, maybe just 1 point or 2 points off. Okay, but most of you didn't get this part. So let's take a break and then we come back and finish the rest. Okay? Have any questions so far? Okay, if not, then we take a break then.